Okay, a little of it aside, we're going to look a little bit at geometry. It's always so finicky. Okay, you see, here's a radius, and here's a radius, and the angle between those two radii is delta. You notice that this tangent is perpendicular to this radius, and this tangent is perpendicular to this radius. There's a geometry theorem, and you probably don't remember all these theorems, but this is a really important one. And those of you who wind up taking statics, you use this all the time in statics, so you really have to make sure it becomes a part of you. When two lines are perpendicular to two other lines, the angle between those lines are equal. It means if this is delta, and delta lies between R, the R and the R line, and the tangent, this tangent line is perpendicular to this R, and this tangent line is perpendicular to this R, it means the angle between these two lines is the same angle as here. So R and R, the angle between R and R is delta, and because this tangent is perpendicular to this R and this tangent is perpendicular to this R, the angle between these two lines that are perpendicular to these is the same as this angle. Okay, so you have to remember that. So now, another thing we need to know. And this one is probably a theorem too, but I have no idea how the theorem is represented. I just know that it's the case. Actually, let me show you something else first. Well, let's talk about something and then we'll come back to this. So if we go back to our picture, and we're trying to think of now how we would set up in the field. You might say with all the things we calculated, maybe we want to set up here. Set up our equipment here. And then we would have an angle off of something, and then we set out our distance of R, 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 and R. And then we can locate where PC is, where the 21 plus 0, 0, 22, 23, and the PT. The only problem, R is pretty far away. It's 303 feet. We can see, using a tripod or a total station, 303 feet. But just imagine you're on Highway 17 and you're trying to set up on the center line of the curve. You're either going to be up in the woods or way down in the woods, and you'll never be able to see those points. So we can't set up on the center of the circle. So what should we do? So something else, I mean, if I was in a classroom, I would wait for your answers, but I'm just going to use the answers that I know that I've been given. So somebody else might say, well, why don't we set up here and then find this point, and then move our equipment to here and find this point, and then move our equipment to here and find this point, and then move our equipment to here and find this point. So how many setups would that be? 1, 2, 3, 4 setups. We already know that setups are the most time consuming, right? So we want to minimize our number of setups. But in addition to it being time consuming, let's say you set up here, you locate this point, and you made a mistake. When you move your equipment to the wrong point, all these other things are going to be wrong. So you're going to keep putting in the error. So it would be best to do something else where if one of them turns out to be an error, you could kind of spot it when you go to put in the circle, the curve rather. So the correct way of actually laying out a horizontal curve is to only have one setup. Only set up at your PC. And then you locate your 21 plus 0, 0, locate 22 plus 0, 0, all from having your equipment here. And then 23, and then the PT. But how do we go about doing that? so we're going to set up right here. If we're able to sight the center line, what kind of angle do I turn to sight the PI? Remember, the PI is where the two tangents intersect? What's this angle right here? What's the angle between the tangent and the center of the circle? 90 degrees. Now, we already said that it may be difficult to find the center of the circle, right? But we always have, oh, I said PT, I meant PI, sorry. We always have our PI. Our PI isn't really that far from where our curve is. So we can always find that point. So whenever we do a setup, we always sight that, and this becomes our 0, 0 angle. And then we look at these sections. We still have section 1, which is this piece, to find 21. Now, how am I going to find 21? We know already in surveying that we turn an angle, and then we lay out a distance. Do we have the horizontal distance from the PC to 21 plus 0, 0? Yeah, we do. We have that chord length, right? We have that little chord length. But what angle are we going to turn? If we have our equipment sighted on the PI, the direction of the PI, I need to know what the angle is between the PI line and the chord line. So let's pull back this. This is where it's taking us into geometry again. And again, I don't remember the exact theorem. So notice I'm setting up on PC, I'm sighting the PI, and I'm trying to find this angle between the PC to PI line and the PC to the PT, because I know what this chord length is. This right here is called the deflection angle. And the deflection angle is little delta, and I'll show you what the symbol is for it. So it's half the included angle. So even though we learned that this delta here and this delta here, these are the same values, the angle between the tangent and the chord to the end of the curve is equal to half of the interior angle. And let me show you another slide that shows this as well. Okay, this is a completely different problem. But here's our PC. It happens to have a station of 12 plus 6250. Here's station 13. Here's station 14. Our little d right here, D1, is 3 degrees. Remember, this is a different problem, completely different problem, different numbers. Just another example. This little interior angle here is 3 degrees. So that means when I'm at the PC and I'm sighting the PI, and I turn an angle to find the second station, the chord, it's going to be, this is lowercase delta. Lowercase delta, it's half of 3. Let's look at this big thing now. What's this total included angle here? 11, right? So that means when I sight the PI, and now I'm sighting this next station of 14, this angle right here is going to be half of that whole thing, which would be 5 degrees, 30 minutes. So let's go back. Okay. When I talked about delta, you know, in our English language, we have lowercase letters and uppercase letters, right? Well, so do they in the Greeks do too. So this is little delta, and this is capital delta. This is little sigma, and this is capital sigma. I don't know how much further I could go.
I definitely can't.
Epsilon, I think this is epsilon, and I think it's capital E. But you guys probably, some of you are already on your,
I think they probably know
on your
more
phone.
than we do.
So, okay. So here we're looking at so if I'm set up on the PC, I cite the PI, I turn the deflection angle 1, which is equal to what? D1 over 2. And then I measure out the chord length. So the question then is, how do I find the second station? Don't I need to look at kind of the double slice of the pizza? Now, this angle right here is D1 plus D2. And here's my chord length. And if you can't add C1 and C2, right?
Mm-hmm.
C is going to be less than C1 or C2.
Right.
Less than C1 plus C2. And then I have to find my new deflection angle, which is going to be half of D1 plus D2. So let's go back to our table. So we looked at the top part of the table, and we looked at the section. There was 4 sections here. And for each section, we found the interior angle, the arc length, and the chord length. And now we're looking at the cumulative. So I'm calling them cumulative because now we're summing them up. Section 1 is still, sorry, I'm not remembering the numbers.
Joanne, before you start filling it in, can you actually put the table down just a little bit so that bright spot?
Good?
Yeah, much better.
Okay, so it says cumulative. How's that? So section 1.
Oh, batteries. Let me just. Sorry, you guys. Just a minute.
Oh, that's okay. Let me.